Welcome to The Deep Dive. Today we're venturing into, well, the pretty fascinating world of particle physics.
hmm
Specifically, we're looking at YangMills theory. Now, that name, it might sound a bit complex,
It can, yeah.
but this is really a foundational framework.
Yeah.
It describes how the universe works at its most basic level. We're talking the strong and weak nuclear forces here.
Pretty much the operating system for a lot of reality, you could say.
That's a good way to put it.
Yeah, it's a theory with just incredible explanatory power,
Yeah.
when it comes to how elementary particles interact.
There's a but, right?
There is. It still holds some really, really deep puzzles. It's a cornerstone, absolutely, but one where some fundamental pieces are still being very actively investigated.
Right. So we've sifted through quite a bit of dense research for this, lots of summaries, trying to get the essence.
Yep.
And our goal today for you listening is really to give a clear understanding of what YangMills theory is about, why it's so pivotal, and maybe most interestingly, what some of the big open questions still are.
We want to illuminate, definitely not overwhelm.
Exactly. Okay, let's jump right in then. At its heart, what is YangMills theory?
Okay, so at its core, Yang-Mills theory is what we call a gauge theory.
Gauge theory. Okay.
It's basically the mathematical language physicists use to describe fundamental forces. Now, what makes Yang-Mills special, or different, is that it's built on something called non-abelian Lie groups.
Non-abelian Lie groups. Right, that sounds abstract.
It is. They're a specific kind of continuous symmetry group, and they are absolutely crucial. They dictate the really rich dynamics of the theory.
Okay, non-abelian. Can we maybe relate that to something we might know a bit better, like electromagnetism? Is there a connection?
Oh, absolutely. That's a really excellent way to approach it. You could definitely think of Yang-Mills theory as a, let's say, more sophisticated cousin of Maxwell's theory of electromagnetism.
Ah, okay.
Because electromagnetism, that's also a gauge theory, but it's based on a simpler group, an abelian group called U1. The key distinction is that non-abelian part.
Right, so what's the big deal about being non-abelian? What does that change fundamentally?
Well, the non-abelian nature, it has this really profound consequence. It means the force carriers in Yang-Mills theory, we call them gauge bosons.
Gauge bosons, right?
They themselves carry the fundamental charge of the interaction they mediate.
Wait, so the messengers carry the message's property?
Exactly. Now, contrast that with electromagnetism. Its force carrier is a photon, right?
Yeah.
And the photon doesn't carry electric charge. It's neutral.
Okay.
But in Yang-Mills theories, you often have multiple types of charges like color in the strong force, and the gauge bosons, the force carriers, they actually interact with each other.
They talk to each other.
They do. This self-interaction, it comes directly from the non-commutative nature of those underlying symmetry groups. Like, think of operations where the order you do them in actually matters. A times B isn't necessarily B times A.
Ah, okay. Got it.
And that leads to far more intricate, nonlinear behavior. It's much more complex than electromagnetism. Imagine, messengers who also chat amongst themselves, and those chats change the messages being delivered. That's kind of the flavor.
Wow, okay. That idea of interacting messengers, that really is a shift. So how did this whole concept even come about? What problem were physicists actually trying to solve back then?
Right, so you have to go back to the early 1950s. The big puzzle then was the strong nuclear force.
Holding the atom's nucleus together.
Exactly. And physicists were finding more and more particles, these hadrons, protons, neutrons, and a whole zoo of others. They were trying to figure out the force holding the nucleus together, and they saw patterns, hints of underlying symmetries.
Symmetries, like things staying the same even if you change something.
Sort of, yeah. Like something called isospin symmetry. Think of it as a mathematical way to say protons and neutrons look really similar from the strong forces point of view, almost like two states of the same thing.
Okay, isospin symmetry, that was a clue.
A major clue. You see, quantum electrodynamics, QED, had been incredibly successful explaining electromagnetism using this principle of local U1 gauge invariance.
Local, meaning it could be different at different points in space and time.
Precisely. The idea that physics looks the same even if you change, say, the phase of an electron's wave function differently everywhere. So Chen-Ning Yang and Robert Mills, they thought, what if we apply this local idea to isospin symmetry?
Ah, make that symmetry local too.
Exactly. That was the core insight. In 1954, they published this groundbreaking paper. They proposed promoting that global isospin symmetry, which was assumed to be the same everywhere, to a local one. But here's the kicker.
Yeah.
To keep the laws of physics working, to keep them consistent when these symmetries changed locally, they found they had to introduce new force fields.
They were forced to invent new forces by the math.
You got it.
Yeah.
What we now call Yang-Mills fields and the associated force-carrying particles.
Oh,
It was a mathematical necessity to maintain local symmetry.
incredible. But wasn't there a problem? Didn't you say something about mass?
Yes, there was a big initial hurdle, a major roadblock, really. The theory, as they first wrote it down, predicted these new force bosons would be massless, like the photon.
Okay.
But experiments already strongly suggested that the strong and weak nuclear forces were very short range. And a short-range force implies that its carrier must be massive. A massless carrier like the photon leads to a long-range force, like electromagnetism.
So theory said massless, but reality needed massive. Ouch.
Big ouch. It was a significant issue. Apparently, Wolfgang Pauli, the physics giant,
Of course.
he'd explored similar ideas even earlier, but dropped them. Why? Precisely because of this mass problem. He couldn't see how to get massive carriers out of it.
Oh, the massless particle problem. Okay, that does sound like a fundamental challenge they had to overcome later. So let's dig a bit deeper into the theory itself now. What are the key pieces, the concepts we need? You mentioned gauge groups earlier.
Yes, right. The gauge group is, fundamentally, the symmetry that the theory is built on. It's a mathematical group that tells you how the charges of the theory transveral, how they change under symmetry operations.
Okay. Can you give an example?
Sure. So for quantum chromodynamics, or QCD, that's our theory of the strong force.
Right.
The gauge group is SU3. And the charge isn't electric charge. It's what physicists call color. It comes in three types: red, green, and blue. And quarks are the particles that carry this color charge.
Color charge, okay. And for the other forces?
Well, for the Electroweak Theory, which bundles together the weak force and electromagnetism.
That unifies them?
Exactly. The gauge group is a bit more complicated. It's SU2L times U1Y, different symmetry, different charges involved.
Got it. So the group defines the symmetries and the charges. What about the actual particles, the fields in the theory?
Okay, so broadly you have two types. You have the matter fields. These represent the fundamental particles like quarks, electrons, neutrinos.
The building blocks.
They carry the charges defined by the gauge group, and how they behave mathematically is dictated by that group. Then, crucially, you have the gauge field, also sometimes called the connection.
That's the force carrier.
That's the force carrier field, yes.
Yeah.
Like the gluons for the strong force, or the W and Z bosons for the weak force. Its whole job, mathematically speaking, is to ensure the theory stays consistent or invariant when you perform those local gauge transformations we talked about.
Making sure the rules don't break when the symmetry changes locally.
Precisely.
And how does the math actually handle that? You mentioned things changing from point to point.
Ah, yeah. That's where something called the covariant derivative comes in. It's basically a modified version of the regular derivative you learn about in calculus.
Modified how?
It's modified to take into account how the gauge field itself changes under these local symmetries. Think of it like this. When you're measuring how a matter field changes from one point to the next in a theory with local symmetry, you can't just look at the matter field. You also have to account for the twist or rotation introduced by the gauge field at each point.
So it's like a derivative that knows about the local symmetry environment.
That's a great way to put it. It keeps the physics consistent, keeps the equations working correctly, regardless of those local changes in symmetry.
Okay. And there was another piece you mentioned, the field strength tensor, analogous to electromagnetism.
Yes, the field strength tensor, often written F-mu Fu. It's very much like the electromagnetic field tensor in Maxwell's theory. It tells you the strength, the intensity of the force field at any point in spacetime.
But there's a difference in YangMills.
A huge difference. In Yang-Mills theories, the formula for the field strength tensor includes extra terms, crucial extra terms that involve the commutator of the gauge fields. The commutator, that thing related to the order mattering, A times B minus B times A.
Exactly that. This commutator term is zero in abelian theories like QED, because the order doesn't matter, things commute. But it's non-zero in YangMills theories. And it directly reflects that self-interaction of the gauge bosons we discussed.
Ah, so that mathematical term, that non-zero commutator, is the signature of the force carriers interacting with themselves.
It is. It's the mathematical embodiment of that key physical difference. It's a defining feature.
Okay, and all this gets wrapped up. How? Is there one master equation?
Well, the whole theory, all its dynamics, is usually encoded in something called the Lagrangian density, or just the Lagrangian.
Lagrangian. Heard of that?
Yeah, that's a central concept in physics. It's basically a mathematical expression that acts like the fundamental rule book for the system. You derive the equations of motion from it. For YangMills theories, a key part of the Lagrangian involves a mathematical operation called the trace, applied to the square of that field strength tensor, FUM. Okay, wow. That's quite a theoretical structure. Gauge groups, matter fields, gauge fields, covariant derivatives, field strength tensors with commutators, all tied up in a Lagrangian.
That's the core machinery, yes.
So how does this abstract math connect to the actual forces we see? We touched on the standard model. How central is YangMills to that?
Oh, it's absolutely central. You really can't overstate it. YangMills theory provides the fundamental structure for our most successful descriptions of 3 out of the 4 fundamental forces: strong, weak, and electromagnetic. Gravity is the odd one out for now.
Right. Okay, let's take the strong force first. That's governed by quantum chromodynamics, QCD, you said.
Exactly. QCD is a Yang-Mills theory. The gauge group, as we mentioned, is SU3.
SU3. And the charge is color.
Right. 3 types: red, green, blue.
Yeah.
And combinations anti-colors, too. Quarks are the matter particles that carry these color charges.
And the force carriers, the messengers for the strong force.
Those are the 8 gluons.
Yeah.
They are predicted to be massless in the basic theory. But here's where it gets really, really interesting, tying back to that self-interaction.
Yeah.
The gluons themselves also carry color charge.
The gluons have color.
They do. It's not just red, green, or blue, but combinations. Like a gluon could carry red and anti-green simultaneously.
Oh.
So this means gluons interact directly with other gluons. This self-interaction is a direct consequence of that non-abelian SU3 gauge group. It makes QCD profoundly different from QED, from electromagnetism.
So the glue holding the nucleus together is itself sticky, so to speak.
That's a perfect analogy, yes. The particles mediating the strong force are also subject to the strong force.
That sounds like it would lead to some unique behaviors, really complex stuff.
It absolutely does. And it's this gluon self-interaction that's believed to be responsible for some of the most fascinating and frankly weird phenomena in all of particle physics.
Like what?
Like why we never ever see a free quark or a free gluon flying around on its own. They're always bound up together inside composite particles. Hadrons, we call them protons, neutrons, pions, etc.
They're trapped.
Essentially, yes.
Yeah.
It also leads to 2 concepts that sound almost contradictory: asymptotic freedom and color confinement.
Asymptotic freedom and color confinement. Okay, those sound important. And yeah, a bit opposing. Can you unpack those briefly?
Sure. Asymptotic freedom is the idea that when quarks and gluons are really close together, like at very high energies in a particle collider,
Yeah.
the strong force between them becomes surprisingly weak.
Weaker when they're closer. That feels backwards.
It totally does,
Yeah.
but it's true, and it's incredibly important because it means physicists can actually do calculations using techniques called perturbation theory for high-energy processes. They can predict things quite accurately.
And that was a big deal.
Huge deal. This discovery earned David Gross, David Pulitzer, and Frank Wilczek the Nobel Prize in Physics back in 2004. It was a crucial insight.
Wow. Okay, so that's asymptotic freedom. Weak force at short distances. What about the flip side? Color confinement.
Color confinement is what happens at low energies, or equivalently larger distances, when you try to pull quarks apart.
Like stretching that sticky glue.
Exactly like that. The strong force between them doesn't get weaker like electromagnetism or gravity would. It actually gets stronger. Or at least the potential energy stored in the field between them keeps increasing.
Stronger as they get further apart.
The potential energy does, yeah. The idea is that it would take an infinite amount of energy to pull them completely apart, so they stay confined. Quarks and gluons are perpetually trapped inside those color-neutral composite particles, the hadrons. We never observe a particle with a net color charge.
So we see the effects of quarks and gluons, but never one by itself.
Precisely. Now here's a key point. While we observe confinement, and asymptotic freedom help explain how it might work, getting a rigorous mathematical proof from first principles of QCD that shows confinement must happen, that's still missing.
Seriously. We have this incredibly successful theory, QCD, describing the strong force, matching experiments beautifully, but one of its most basic observed features, confinement, we can't fully prove mathematically yet.
That's the situation. It's one of the biggest unsolved problems in theoretical physics.
Yeah.
It's quite humbling, actually.
Absolutely humbling. Okay, let's switch gears to the other force you mentioned fitting the YangMills framework, the Electroweak Force.
Right, the theory that unifies electromagnetism and the weak nuclear force. The force responsible for certain types of radioactivity, like beta decay and processes in the sun.
Also built on YangMills.
Also built on the YangMills framework, yes.
Yeah.
The gauge group here, as I said, is SU2, LXU1Y. A bit more structure. Initially, just applying the Yang-Mills recipe here predicts 4 massless force carriers.
4 massless ones, but wait. The weak force carriers, the W and Z bosons, they're definitely not massless. They're really heavy, right? Unlike the photon.
Exactly. That was the other big mass problem that needed solving. How do you get massive force carriers out of a theory that seems to naturally want massless ones?
So how did they solve it this time? It wasn't just ignored like Pauli maybe did earlier.
No, this time there was a solution. This is where the famous Higgs mechanism comes into play. Peter Higgs and others like Brout and Englert figured this out.
Ah, the Higgs boson we hear about.
Related, yes. The idea involves a pervasive energy field, the Higgs field, filling all of space, through a process called spontaneous symmetry breaking.
Spontaneous symmetry breaking. Sounds intriguing.
It is. Basically, the underlying equations have a symmetry, but the lowest energy state of the system, the vacuum, doesn't fully respect that symmetry. When this happens with the Higgs field interacting with the SU2 LX U1Y gauge fields,
Yeah.
3 of the initially massless gauge bosons combinations that become the W plus the W and the Z0 bosons, they interact with the Higgs field in a way that effectively gives them mass. They acquire inertia by plowing through this field.
Wow. So the Higgs field gives them mass.
That's the common picture, yes. And crucially, one combination of the original gauge fields remains massless. And that combination is
the photon.
the photon, exactly. So the Yang-Mills structure, combined with the Higgs mechanism, provides this absolutely stunning explanation. It unifies the weak and electromagnetic forces and explains why the W and Z are massive while the photon isn't.
That is incredibly elegant.
It really is. And so the whole Standard Model, our best description of fundamental particles and forces so far, excluding gravity, is built on this combined gauge group, SU3C for the strong force, QCD, and SU2LXU1Y for the electroweak part, all underpinned by Yang-Mills principles plus the Higgs mechanism. It's a monumental achievement.
Truly monumental. Okay, so Yang-Mills theory is this fundamental bedrock. But you mentioned lingering questions earlier. Beyond just proving confinement, there was the mass gap. What exactly is the mass gap problem?
Yes. This is one of the deepest and hardest open problems. It sits right at the intersection of physics and pure mathematics.
Okay.
So even though the classical Yang-Mills equations, the ones Yang and Mills first wrote down, allow for solutions that look like massless waves propagating.
Like light waves, sort of.
Sort of, yes. But the full quantum version of the theory, which is what we need to describe reality, is expected to behave differently. It's expected to have a mass gap.
A mass gap, meaning?
It means that the lowest possible energy state above the vacuum being the state of truly empty space with the absolute minimum energy possible.
Yeah, the ground state.
Right. The very first excited state, the lightest possible particle or excitation you can create in the theory, should have a mass that is strictly greater than 0. There should be a gap between the 0 energy of the vacuum and the energy of the lightest possible particle. Its mass, delta, must be positive.
So even if the basic building blocks, like gluons, start out massless in the equations, the actual physical particles that emerge from the complex quantum interactions, they should all have some minimum mass. No massless excitations allowed in the full quantum theory, except maybe in very special cases.
That's the expectation, particularly for pure Yang-Mills theory, or QCD, in our 4 dimensions, 3 space, 1 time. It's believed that even the gluons, through all their self-interactions and the quantum weirdness, effectively generate a mass scale. Proving this rigorously, well, that's the challenge.
Yeah, and this is a big deal.
Huge. Proving rigorously, first, that a mathematically consistent, non-trivial quantum Yang-Mills theory actually exists on our 4D spacetime, and second, that this theory does possess such a mass gap. That is one of the 7 Millennium Prize problems announced by the Clay Mathematics Institute back in 2000.
The Millennium Prize problem. Wow. That really tells you something about the difficulty and importance. $1 million prize attached to it.
Exactly. It highlights just how fundamental and how hard this question is.
So what's the status? It's 2025 now. Any progress? Solved yet?
Officially, no. Still unsolved as of our recording in April 2025. There's been progress in related, sometimes simpler settings. Like, I remember seeing work, maybe around 2020, making headway on understanding related mathematical structures, like something called stochastic Yang-Mills heat flow, but that was in 2 dimensions.
2 dimensions, not our 4.
Right. The jump to 4 dimensions is notoriously difficult. The quantum field theory becomes much wilder mathematically.
What about other approaches? Simulations?
Oh, yes. Lattice gauge theory, where you replace continuous spacetime with a grid, a lattice, and run massive computer simulations.
Yeah.
That provides very strong numerical evidence for the existence of a mass gap in theories like QCD. The simulations consistently show that the lightest states, like particles made purely of gluons called glue balls,
Glue balls. Particles made of just the force field.
theoretically,
Yeah.
yes, predicted by QCD. The simulation suggests these glue balls have mass, consistent with a mass gap.
But simulations aren't mathematical proof?
Correct. They're incredibly powerful evidence, guideposts, but they don't satisfy the requirements for a rigorous mathematical proof, starting from the fundamental axioms. Plus, even within lattice QCD, accurately calculating the full spectrum of glue ball masses and properties and comparing them definitively with experimental hints, like maybe the mysterious sigma meson, is still really challenging and involves ongoing debate.
So strong hints, strong evidence from simulations, but the airtight proof remains elusive.
Precisely. And just to add another wrinkle, there was actually some recent buzz, I think a paper came out in 2024,
Oh, yeah.
that claimed to find conditions based on looking at energy-momentum relationships where a mass gap might not exist. Both in abelian theories, we don't usually expect one anyway, but also potentially in non-abelian theories.
Wait, challenging the mass gap for YangMills?
It seemed to. Now, this goes against decades of expectation, especially for QCD, where the mass gap is thought to be deeply connected to confinement.
Mm.
So that paper is definitely getting a lot of scrutiny from the community right now. Needs careful checking.
Wow. So even this fundamental expectation might have twists and turns. It really shows how active this field still is.
Absolutely.
Now, we've focused heavily on physics, obviously, but you hinted earlier that YangMills theory has had a big impact on pure mathematics, too. How so?
Oh, the interplay is incredibly deep and has been really fruitful. It's one of the prime examples of physics driving mathematical innovation.
How does that connection work?
Well, in the language of differential geometry, a branch of math dealing with curved spaces and shapes the gauge potential, the Yang-Mills field itself.
Yeah.
It can be understood as a mathematical object called a connection on something called the principal G-bundle. These are sophisticated ways mathematicians use to describe geometric spaces that have certain symmetries built in.
So the physics object is a known mathematical object.
It has direct mathematical interpretation, yes. And the field strength tensor, the FUN we talked about, which measures the force.
What's that in math terms?
It corresponds precisely to the curvature of that connection. So fundamental physical concepts like potential and field strength map directly onto fundamental geometric concepts like connection and curvature.
That's amazing. The language of geometry is the language of force fields.
It really is stunning when you see it laid out. And it goes further. In the 1980s, a mathematician named Simon Donaldson did groundbreaking work. He used particular solutions to the Yang-Mills equations, things called instantons.
Instantons.
Yeah, sort of localized lumps of field energy in Euclidean spacetime. He used the properties of the space of these instanton solutions to discover completely new and unexpected facts about the topology of smooth four-dimensional manifolds.
Four-dimensional shapes, like our space-time, but purely mathematical.
Exactly. His work, directly using tools from Yang-Mills physics, completely revolutionized that area of pure mathematics. It showed that 4D spaces are much weirder and more complex than lower or higher dimensional spaces in some ways. He won the Fields Medal, math's highest honor for it.
Wow. Physics ideas changing pure math. That's incredible.
And it continues. More recently, ideas and techniques from gauge theory, from Yang-Mills theory, are becoming increasingly important in another vast, highly abstract area of math called the geometric Langlands program.
Geometric Langlands. Never heard of it.
Well, it's pretty advanced stuff.
Yeah.
But it aims to build deep, unexpected bridges between seemingly very different parts of mathematics, like number theory, geometry, and the theory of symmetry representations. And gauge theory concepts are proving to be surprisingly useful tools in that quest.
It's just mind-boggling. A theory cooked up to explain subatomic particles ends up having profound echoes in the most abstract realms of geometry and number theory.
It truly highlights this incredibly deep, almost mysterious connection between the physical world and mathematical structures. Yang-Mills theory, both in its successes and its profound open questions like the mass gap, is just a stark reminder of that.
A reminder that physics and math are maybe two sides of the same coin, exploring the same deep reality.
Perhaps. It certainly shows how exploring the fundamental building blocks and forces of our universe pushes the boundaries of mathematics, and how mathematical insights can, in turn, illuminate physics. It's a two-way street.
This has been absolutely fascinating, a real deep dive into Yang-Mills theory. So just to try and wrap up the key takeaways for everyone listening,
Okay.
We've seen YangMills theory is this incredibly successful framework, right? It's the bedrock of the standard model, explaining the strong and weak forces using these ideas of local gauge symmetry.
And those crucial self-interacting force carriers, the non-abelian nature, don't forget that.
Right, the messengers talking to each other, that's key. But despite all its successes, huge mysteries remain, proving confinement rigorously, and especially proving the existence of that mass gap in the quantum theory.
Exactly. We saw how those self-interacting gluons in QCD lead to these amazing counterintuitive phenomena like asymptotic freedom getting weaker up close and color confinement getting stronger far apart.
Yeah.
And the fact that this theory, which works so well describing reality, also poses these incredibly hard million-dollar problems for mathematicians.
Yeah.
That's just remarkable in itself.
It really makes you pause and think, doesn't it? Here's a theory, arguably one of our most fundamental descriptions of nature, yet it contains these deep, unsolved mathematical questions at its very core. What does that say about, the limits of what we currently understand?
Mhm.
And maybe it suggests that other areas of science, things we think are neatly wrapped up, might also harbor similar hidden depths or unresolved foundational issues if we look hard enough.
That is a wonderfully provocative thought to end on. It speaks to the ongoing adventure of science. There's always more to understand, potentially fundamental things we haven't grasped yet.
So if you listening want to explore this further, where should you look?
Well, for the adventurous, looking into resources on lattice QCD simulations could be interesting to see how physicists get numerical evidence. Or for the mathematically inclined, checking out the official description of the YangMills existence and mass gap problem on the Clay Mathematics Institute website would give you the precise formulation. It's a journey into the heart of modern theoretical physics and mathematics.
Fantastic. Well, thanks for guiding us through that complex territory.
My pleasure. It's fascinating stuff.
Thanks for joining us for this deep dive. Until our next exploration, keep questioning.